The math for this week's lab seems a little daunting, so let's go through how to find the answers. This is a diffraction grating. There's a piece of photographic film here with thousands upon thousands of tiny little lines scribed into it. Now what those lines do is when light enters the diffraction grating, it is bent. So the incident angle and the exit angle are different from one another. This allows us to split mixtures of light into their individual colored components. If this is white light from sunlight, I get the full rainbow. If this is the emission from an atom, I get quantized energy levels and I see line spectra. Okay, the diffraction gratings work on this equation. This is the Bragg equation that says that lambda equals d sine theta. Lambda is the wavelength in meters. Most times when we talk about wavelength of visible light, we're going to be talking in nanometers, which is 10 to the negative 9 meters. We're going to need to change our nanometers into meters. The angle here that the light is bent is just represented as a degree. D is the line spacing of the lines that are inscribed on this film. And if we find the value of D, because each individual grating is going to have its own value, if we find the value of D, then we can always relate the angle of diffraction, which we can measure, to its wavelength. So I can take a light that I don't know, I've previously not seen before, measure its diffraction angle, I know the value of D, I can find the wavelength of that light. Okay, here's how we're going to do that. It's a little involved. First, we're going to work with a light that we already know. We're going to start with helium. Helium has an emission spectrum that is well studied, and the values of the lines are in your report already. The colors and the wavelengths of the emission lines are known. So, we're going to set up a lamp. Here's the eyeball of the viewer, looking through the diffraction grating at a distance from the lamp. As you look through the diffraction grating, off to the side, you are going to see the colored bands of the line spectra. If we have somebody else measure how far away from the lamp the line presents itself, then we've made a right angle triangle. This right angle triangle here has 3 sides and 1 important angle. This side is called the adjacent side. This is the distance from the eyeball to the lamp. This side is called the opposite. It is the distance from the lamp to the line. And then this side is the length that that line is away from the viewer. That's called the hypotenuse. The angle here is theta. Here's where trigonometry comes in. We are going to find that value, theta, so that we can feed it back into this Bragg equation, so that when I know theta, I can know wavelength. Before I can do that, I have to find the missing value, D. So I'm going to rearrange the Bragg angle that D is lambda divided by sine theta. The lambdas are given to you in the lab report. Sine theta is what you are going to find yourself. And we're going to find that first by finding the tangent. The tangent of this angle is the opposite divided by the adjacent. Trigonometry tells us that tangents are opposite divided by adjacent. In our experiment, that value right there is L, and this value here is called D. L, we are going to set to be 1 meter. So D over L, when L becomes 1, is just D. So the tangent of that angle is just the length of that side that you've measured. Now the meter stick is 1 meter long. It reads in increments of centimeters. So you're going to need to convert your centimeters into meters. And also, depending on whether you're looking at the left or the right, it's the distance from the middle. And if you've got the middle set to be 50, you're going to need to take into account it's this distance. Okay, so if tan theta equals this value D, then we can get to theta by taking the inverse tangent of the tangent. On your calculator, you're going to have a button that says tangent. The first function, the shift function of that tangent, is the inverse tangent. And if you take the inverse tangent of the tangent, you just get the angle, theta. So, we just found the value of the angle theta. Along with tangents and cosines, there are sines. So you take the sine of theta and then you feed it in to this equation and it gives you D. Once we know D, we can switch out the lamp and do the experiment again, this time on hydrogen. The hydrogen emission spectrum is also quite well known, but we're going to go and explore something very special, because these quantized line spectra, they obey mathematical rules that we wouldn't suspect, and those rules are quite simple. So we're going to switch the lamp out for hydrogen. We're going to do exactly the same type of experiment, but now I know the value of D. I know this value, D, the line spacing. D is how far apart those lines are on the diffraction grating. We're going to measure the blue line, the green line, and the red line, and we're going to go opposite over adjacent to find the tangent of theta. We're going to take the inverse tangent to find theta, and we're going to take the sine of it to find sine theta. So now we know this number, and we know those numbers, and we get to find the value of the wavelength of the emission lines for the hydrogen emission spectrum. Okay, turns out Rydberg figured out that the inverse of wavelength, which we also call wave number, is equal to a constant that he named after himself, multiplied by this term, 1 over the first value of n squared minus 1 over the second value of n squared. And those values are on the front page of our lab report for today. Hydrogen has a very simple electronic structure, and every time you excite the atom by giving it lots and lots of electricity, it promotes an electron from a ground state to an excited state, and when those electrons come back, they emit the difference in those energy states. There are 3 sets, one in the infrared, one in the visible, and one in the ultraviolet. The visible light, the Balmer set, follow this rule, that they move from the value where n equals 2 to n equals 3 for red light, from n equals 2 to n equals 4 for green light, and from n equals 2 to n equals 5 for the blue light. So if we wanted to know what the value of this Rydberg constant is, this constant that holds all of this together, I just take this term and move it over, so that the Rydberg constant is 1 over the lambda multiplied by this term. Okay, so for the red light, just the red component. The red component moves from 2 to 3. So here's a 2, and there's a 3. This is the wavelength for the red light that you've already measured. So the Rydberg constant would be the reciprocal of the wavelength multiplied by 1 divided by 2 squared, which is 4, and you subtract from that 1 over 3 squared, which is 9. And it turns out that this complicated quantized world of emission spectra follows a very rigid trend.